Yesterday in class, well, some of you were at the soccer game, we covered waves, notes on waves, and calculations involving wave functions. So today, I want you to catch up by watching this short video on waves, their properties, and how to do calculations with them. So you might remember in ninth grade talking about some of these things. As this video progresses, you might see things that sound vaguely familiar, hopefully. If you look at the first type of wave, okay, a wave is a way of transferring energy, okay? So a wave is a way of transferring energy, and there are two different kinds of waves that can occur. The first is a compressional wave, which is kind of like taking a slinky and smushing it back and forth so that you have compressions and then areas where they are spread out, and then more compressions. Okay, when a compressional wave is traveling, the matter is traveling from side to side. And these kinds of waves do require a medium to travel through, like air or water, or even a solid. Sound can travel through a solid. And as I just said, an example of a compressional wave is sound waves. Now, the other kind of wave, the wave that we care most about for our studies in chemistry, is called a transverse wave. And a transverse wave looks a little different. A transverse wave starts by going up and then down and then up again and then down and then up. And you can kind of repeat this. This center dotted line is what we would call the resting position. So the motion of the matter is up and down, kind of like the waves on a lake. Now, these do not require a medium to travel through. And so light is a good example of a transverse wave. Light can travel through outer space from the sun to us on Earth, and it can get there without a medium. However, sound could not travel in outer space because there's no atmosphere or air for it to travel through. Okay, so maybe this is familiar from ninth grade, but there are two kinds of waves: compressional, where the motion is back and forth, and transverse, where the motion is up and down. Transverse are the ones that we are going to study the most in chemistry because those are the light waves that we're going to focus on. Now, if we look at a transverse wave a little bit more closely and we draw a bigger example of it, we're going to label some parts. Now, this dotted line again is the resting position. Now, the height from the resting position to the tallest point on a single wave is called the amplitude. That same height is, and it's probably not drawn very accurately here, but that same height amplitude above the resting position should be the same as it is below the resting position. The point up at the top, the highest point, is called the crest, and the lowest point is called the trough. Now, if I were to flip this wave upside down, the crest would become a trough, and the trough would become a crest. Okay. Now, if I were to pick any point on a wave, and I'll do this in a blue marker here, if I start at this point here and I trace it through all the way up one cycle and down one cycle back to that starting resting position, repeating, it has to go up then down, that is considered one wave. And if I measure the distance between that point, that is called a wavelength. Wavelength could also be measured from one crest to another, as long as it's going through one period. So that's a wavelength. Now, if I were to draw one wave with a very short wavelength, I'll call that wave wave A. Notice the waves are close together, therefore it has a short wavelength. Compare it to wave B, which I'll draw here. that has a much longer wavelength. What you'll notice is that the waves in A are squished much closer together. There are more waves in A than there are in B. So we would say A has what we call a high frequency because there are a lot of waves in that time frame, versus B, which has a low frequency. Now, those are terms that we want to look at more carefully because those are the terms that are going to appear in when we do some math problems with this. So wavelength, again, to get a definition down, is the distance from a crest on one wave to the crest on the adjacent wave, the one right next to it. Now, that unit for wavelength, since it is measuring a distance, should be in meters. So whenever we deal with wavelengths, we want them in meters. Sometimes our problems will give them to us in centimeters. If it's given in another unit, you will have to convert whatever it was to meters. Wavelength needs to be in meters. Frequency, on the other hand, is the number of waves passing through a given point in 1 second. So if 8 waves pass through a given point, we would say it has a frequency of 8 waves per second. Now the unit on that one is a little tricky. Per second means that the second is in the denominator. So we would say 1 over s, s being seconds. Now from math class, you should know that 1 over anything is the same as that s. In this case, 1 over s is the same as s to the minus 1. Now, in science, we give this unit a special name. It is called a hertz. So oftentimes you will see it written as Hz. We might say the frequency of the wave is 1,000 hertz, but that just means 1,000 waves per second. Now, if you look at a radio dial, okay, FM stations have frequencies of megahertz. So for example, K102 has a frequency of 102.1. That's where you would find it on your dial. What that really means is that 102.1 mega or million hertz or waves per second. So K102 has 102.1 million waves per second versus say 93X, 93.7 has 93.7 million waves per second. That's how your radio receiver knows which one you're dialing into. On the other hand, AM radio stations are in kilohertz. So if you look at something like 830 WCCO, it has a frequency of 830 kilo or times 10 to the 3,000 hertz. Okay. So FM radio stations are broadcasting at a higher frequency than AM radio stations. Now, how does all this work into a formula? Well, if you, we're going to use wavelength and frequency to calculate speed. So you can see up here that the speed of a wave is equal to the wavelength times the frequency. Now, from 9th grade, speed is often the same as velocity. So we're going to call that V. These are the symbols that we are using. Okay, V is equal to, now wavelength has a strange Greek letter called lambda. It sort of looks like an upside down Y. Wavelength is lambda times frequency looks like a funny looking V, which we call the Greek letter nu. Wavelength equals, or wavelength times frequency equals the speed of a wave. Now the units that we always want things to be in, okay, if you think about wavelength, we always want that to be in meters. And with frequency, even though it is given in hertz, it's more helpful to think of it as 1 over s. And if you take meters times 1 divided by s, you will end up with a label for speed of meters per second, which should make sense to you. So now you have all the tools in order to do a speed calculation for a wave. Many waves, however, travel at the speed of light. And so in order to know how to calculate those kinds of things, you need to know the value for the speed of light. This is a big deal. You might want to make a big box around this in your notebook. 3.00 times 10 to the 8th meters per second is the speed of light. So I want to make sure you remember that. That's a big one, okay? If a wave is traveling at the speed of light, you will always know its speed, and you'll be asked to find either the wavelength or the frequency. Now we're going to do one practice problem, and then hopefully you should be able to figure out the rest by doing this one. Here's the example. A student is listening to the FM radio station B96 while doing their chemistry homework. This radio station has a frequency of 96.3 times 10 to the 6th hertz. If radio waves travel at the speed of light, what is the wavelength of these waves? Now to start the problem, it's always good to be, it's always smart to be a good bookkeeper. What you're given here is a frequency. Now frequency has that funny letter V or nu, and it is equal to 96.3 times 10 to the 6th hertz. Now a hertz is the same as a 1 over s, and that's going to be more helpful to you when canceling units in your problem. We do know that the radio waves are traveling at the speed of light, which I told you on the previous note page here is 3.00 times 10 to the 8th meters per second. And what I'm asking you to find is wavelength. That's the question mark that we're looking for. So if you go to the notes, you know that the speed of light is 3.00 times 10 to the 8th. Now, I will tell you that we give a special letter C to the speed of light. You might have heard of it in E equals mc squared. Okay, so what we're going to say is that the speed of light, C, is equal to the wavelength times the frequency. Well, what we're trying to find is wavelength. So we're going to divide both sides by frequency. And that's going to give us a formula of wavelength equals the speed of light, C, divided by the frequency. Now, all you have to do is plug your numbers in. The speed of light is 3.00 times 10 to the 8th meters per second. And that is divided by the frequency, which was 96.3 times 10 to the 6th 1 over s. So you do the math, make sure you use your calculator correctly, and when you do that, you should get 3.12 is the number. And then when you look at your labels, the seconds cancel out, so this should be 3.12 meters, which should make sense for a wavelength. So if you look back at your formula, speed of a wave equals wavelength times frequency. I can either ask you to solve for speed, wavelength, or frequency, but you have to know the other two. So you will now be ready to try the homework, the worksheet, and if you have problems, you can always either ask me questions in class before or after school, or check with a neighbor who was here yesterday for class. Good luck.